Class 11th, Subject Physics, 10th chapter, Electrostatics. From this chapter, let us see electric lines of force. An electric line of force is an imaginary curve drawn in such a way that the tangent at any given point on the curve gives the direction of electric field at that point. If a test charge is placed in an electric field, it will be acted upon by a force at every point in the field and will move along a particular path. The path along which the unit positive charge moves is called as line of force, and therefore a line of force is defined as the curve to which a tangent drawn at any point gives the direction of electric field at that point. A line of force is defined as the curve to which a tangent drawn at any point gives the direction of electric field at that point. Then in this case, this curve will represent a line of force for a given test charge. At that time, the tangent drawn at any point, suppose that point A is taken, so at this point the tangent drawn will represent the direction of electric field EA at point A. Now if you consider second point B along the same line of force, then tangent drawn to that point B will represent the direction of electric field at that point B, that is EB. So this curve will represent the line of force for that given test charge. Then the lines of force are purely geometric construction and they have no any physical existence. That means these lines of forces will be imaginary so that they will not be having any physical existence. Now some of the lines of forces for charges are given in the figures. So the first figure represents the electric line of force for an isolated positive charge, that is plus Q. If you consider like this single charge and it is positive charge, then the electric lines of forces will be directed from it in all possible direction and it will be directed away from the charge that is in the outward direction. Similarly, for the negative isolated charge, if you consider single negative charge, that is minus Q, then again the electric lines of forces will be directed in all possible directions, but these lines of forces will be directed towards the charge that is directed inwards. Instead of that, if you consider two opposite charges, that is plus Q and minus Q charge, separated by a finite distance, then these curves will represent the electric lines of forces. In this case again, the electric lines will be originated from this plus Q charge and it will incident on the negative charge, that is minus Q charge. So from plus Q charge, the electric lines of force are now directed in the outward direction, that is away from the charge, while for this minus Q charge, these electric lines of forces will be reaching that negative charge and therefore the electric lines of forces will start from the positive charge and it will end on negative charge. Similarly, instead of that, if you consider the similar charges plus Q or minus Q, then for plus Q charges, for both these electric charges, the electric lines of forces will be directed in the outward direction, while in case of minus Q charges, these electric lines of forces are directed towards the charges. So this will be because if you consider the similar charges, there will be repulsion and therefore the electric lines of forces will not mix with each other. But in this case, there are dissimilar charges, opposite charges, and therefore the electric lines will travel from plus Q charge to minus Q charge. Now instead of the electric charges, if you consider any conductor and the electric lines of forces terminated by that conductor will be as shown. From this surface, the electric lines of forces are directed inwards. For this, in the opposite directed, that is towards the second surface of this conductor, but no electric lines of forces will pass through the conductor, and therefore inside that conductor electric field E will be equal to 0. And now let us see some of the characteristics of the electric lines of forces. So what are the characteristics of electric lines of forces? The first characteristic is the lines of forces originate from positively charged object and end on negatively charged object. The lines of forces originate from positively charged object and end on the negatively charged object. Second characteristic is the lines of force neither intersect nor meet each other. The electric lines of forces neither intersect nor meet each other. That is, no two electric lines of forces intersect each other. Third characteristic, the lines of force leave or terminate on a conductor normally. So the electric lines of force leave or terminate on any conductor normally, that is perpendicular to the surface of that conductor. Then fourth characteristic, the lines of force do not pass through the conductor, but they can pass through the insulators. The electric lines of force do not pass through the conductors, but they can pass through the insulators, and hence inside a conductor the electric field is always 0. Fifth characteristic, the magnitude of electric field intensity is proportional to the number of lines of force per unit area of the surface held perpendicular to the field. The magnitude of electric field intensity is proportional to the number of lines of force per unit area of the surface held perpendicular to the field. Sixth characteristic is the electric lines of force are crowded in a region where the electric intensity is large. The electric lines of force are crowded in a region where the electric intensity is large, and therefore near the charges, in this case the electric intensity will be large, and therefore near or close to the charges the electric lines of forces are crowded together. Seventh characteristic, electric lines of force are widely separated from each other in a region where electric intensity is small. The electric lines of force are widely separated from each other in a region where electric intensity is small, and therefore away from the charges, that is in between the charges, these lines of force are widely separated because electric intensity in that region will be small. Then eighth characteristic will be the lines of force of an uniform electric field are parallel to each other and are equally spaced. The lines of force of an uniform electric field are parallel to each other and are equally spaced. So these are some of the characteristics of the electric lines of force. And now let us see the next term, that is electric flux. What is that electric flux? So we know that the number of lines of force per unit area is called as the electric intensity of that electric field. The number of lines of force per unit area is called as electric field intensity of that electric field. Now, in this diagram we have considered a large surface area S, then electric field will be directed along this, then this horizontal line will represent electric field intensity E. Now let us consider a small surface area ds of this surface area S. Now in this case the surface area ds is not perpendicular to this electric field, that is electric field is not perpendicular to this surface area ds, and therefore one of the components of this electric field E will be perpendicular to this surface area ds, and therefore we have taken this angle theta between the direction of electric field E and the area vector surface area ds. And therefore if this angle is theta, let us draw perpendicular here on this component, and therefore this component will be E cos theta, because this angle is theta. This will become hypotenuse for that right angle triangle, and therefore this side, that is adjacent side, will be equal to hypotenuse E into cos theta, and therefore this component is E cos theta, that is the component of electric field E which will be perpendicular to this surface area ds. And therefore now we will consider the relation, that is electric field E will be equal to number of lines of force per unit area enclosing the lines of force, and therefore the number of lines of force from this formula will be equal to electric field E into area, that is number of lines of force will be equal to electric field E into area enclosing lines of force. Now if you consider that surface area ds, then let angle between electric field E and the area vector ds be theta. Then the electric flux passing through area ds will be given as d phi, that is the number of electric lines of forces passing through area ds. This small area ds will be given as the component of vector E perpendicular to ds into area vector ds, and therefore we can write d phi equal to E cos theta, that will be this perpendicular component, into ds, that is the surface area ds, and therefore we can write d phi equal to E ds cos theta. As it is E ds cos theta, it will represent the scalar product of E and ds, and therefore d phi will be equal to vector E dot vector ds. So this will give the number of lines of forces passing through that surface area ds, and hence if we try to find out the total number of electric lines of forces passing through this whole surface area S, then the total flux through entire surface S is given as, it will be given as phi is equal to integration of d phi, that will be equal to integration of vector E dot vector ds. Electric field intensity E will be constant, therefore it will be taken out of integration, therefore vector E integration ds. Now integration ds, that is sum of all these ds enclosed by this surface S, that will be equal to S, that is vector S, and therefore we can write that phi is equal to vector E dot vector S. So this expression will represent the total number of flux passing through the entire surface area S. Now let us find the SI unit of that flux phi. So SI unit of flux is, it will be equal to SI unit of E into SI unit of S. Now SI unit of E is volt per meter. SI unit of S, that is surface area, will be meter square. 1 meter will get cancelled from this square with this meter, and therefore we will get volt meter as the SI unit of this electric flux phi.